Find minimum in rotated sorted array. Ever seen a sorted array that's been spun around and asked to find its smallest value? Find minimum in rotated sorted array is a true blind 75 staple, often asked at Google and Facebook. It's the kind of problem that exposes whether you truly get binary search. Many candidates panic and reach for brute force, but you'll see how a smart twist lets you solve this in just a handful of steps. Ready to level up your searching skills? Let's go. Let's break down the problem. You're given a sorted array that's been rotated at some pivot, so somewhere, the sequence jumps from high to low. Your goal: find the minimum value in the array, as efficiently as possible. The array contains no duplicates. Now let's assess our options. Brute force means scanning every element, on time. But the array's sorted and only rotated. That's a perfect setup for binary search. The trick? At each step, check if the mid element is greater than the rightmost. If so, the minimum is to the right, otherwise, it's to the left, including mid. This narrows the range fast and gives us O log n time. Here's the structure of our approach. Initialize 2 pointers, left at 0, right at the last index, while left is less than right. Find mid as the average of left and right. If num's mid is greater than num's right, the min is to the right of mid, so move left to mid plus 1. Else, the min is at mid or to the left, so move right to mid. When the loop ends, left points to the minimum.
Let's try to implement it using solution 1. We begin by defining the solution class. This is simply the container that holds our method. Next, we declare the findMin method. This method takes an array that was originally sorted and then rotated, and our goal is to return the smallest number in that array. We start by initializing a variable called m to the first number in the array. This gives us a baseline for tracking the minimum value. After that, we loop through every number in the array, one by one. For each number, we compare it with our current minimum. Since we check each element exactly once, this process runs in linear time. Inside the loop, if the current number is smaller than m, we update m to this new value. You can think of this like scanning a list and always keeping note of the smallest value you have seen so far. Once the loop finishes, we return m. This value represents the smallest element in the entire array, and that's how this algorithm works. It starts by assuming the first element is the minimum, then scans through the array and updates that minimum whenever a smaller value appears. Simple, reliable, and easy to reason about. Check. Let's walk through a test case for finding the minimum element in a rotated sorted array. Nums equals 3, 4, 5, 1, 2. This array was originally sorted in ascending order, then rotated. The sequence begins by increasing from 3 to 4 to 5. Then it suddenly drops to 1, and increases again to 2. That sharp drop from 5 to 1 tells us that 1 is the smallest value in the array. The output is 1, which matches the expected answer. This confirms that the solution correctly finds the minimum element in a rotated sorted array. Now let's try another implement approach using solution 2. We begin by defining the solution class. This is simply the container for our optimized method. Then we declare the findMin method. It takes in the rotated sorted array and returns the smallest element inside it. Next, we set up 2 pointers. L starts at the left end of the array. R starts at the right end. These pointers mark our current search window. After that, we begin a binary search loop. We continue while L is less than R. Because we cut the search space in half each step, this runs in log(n) time. Inside the loop, we compute the midpoint between L and R. This is the index we inspect to decide which side contains the minimum. Then we compare nums at mid with nums at R. If nums at mid is greater than nums at R, the minimum must be to the right of mid, so we move L to mid plus 1. Otherwise, nums at mid is less than or equal to nums at R, which means the minimum is at mid or to the left, so we move R to mid. This continues until L and R meet. When they converge, that index points to the minimum element. Finally, we return nums at L, which is the smallest value in the rotated array. And that's how this algorithm works. It sets left and right boundaries, then uses binary search to throw away half the array at a time based on a midpoint comparison, until it lands exactly on the minimum. Efficient, simple, and elegant. Check. This test case also asks for the minimum element in a rotated sorted array. Nums equals 4, 5, 6, 7, 0, 1, 2. This array was originally sorted, then rotated. The values rise from 4 to 5 to 6 to 7. Then the sequence drops to 0, and rises again to 1 and 2. That drop from 7 to 0 marks the rotation pivot. The value at that pivot, which is 0, is the minimum in the entire array. The output is 0, matching the expected 0. This confirms the solution correctly, identifies the rotation point, and returns the smallest element.
Let's have a quick recap. Breakdown recap. This problem gives you a sorted array that's been rotated at some unknown pivot, and your task is to find the smallest element. It's a clever twist on a basic searching challenge. The array is still mostly sorted, but the rotation creates a breakpoint where the minimum hides. Assess recap. At first, it's tempting to scan the whole array, but that's ON time and far too slow for large inputs. The key realization is that this is still a binary search problem. We can use the order properties to cut the search space in half at every step. By comparing the middle and right elements, we can quickly tell which half contains the minimum. Structure recap. Our plan uses 2 pointers, one at the start, one at the end. We repeatedly calculate the midpoint and decide whether to search the left or right half based on how the mid compares to the rightmost value. Each comparison moves our boundaries closer to the smallest number until they converge. Implement recap. In the implementation, this logic unfolds as a looping process. The midpoint comparison guides the movement of the left and right pointers, steadily shrinking the window. When they meet, that shared index points directly to the smallest element, no extra checks or scans needed. Check recap. When tested with the sample array, the algorithm zeroed in on the correct value almost instantly. Each step eliminated half the possibilities, confirming the expected result with impressive speed. It's a perfect demonstration of how binary search adapts beyond just finding specific numbers. The real lesson here is that binary search is a mindset, not just a method. Once you start recognizing patterns of order and pivoting logic, you can use it to solve a wide range of problems elegantly and efficiently. Master this, and you'll think like an algorithmic pro in every interview.